Zero-shot material transfer from a single image. In this presentation, we will explain ZeST, a method for transferring the material appearance of one image onto an object in another image. We will start with the foundational concepts, then discuss why material editing in 2D images is challenging, and finally delve into the ZeST pipeline, results, and implications. Throughout, we will aim for clarity and academic rigor, assuming the audience has no prior exposure to these specific concepts. Foundational concepts. Diffusion models. Modern image generation often uses diffusion models. A diffusion model is a type of generative neural network that starts from random noise and gradually denoises it to produce a coherent image. Intuitively, it works like an iterative process, beginning with pure noise. It takes many steps where at each step it refines the image, guided by learned patterns, until a clear image emerges. Diffusion models have achieved state-of-the-art results in generating photorealistic images, often matching or surpassing GAN-based approaches. They can produce images with realistic geometry, textures, and lighting conditions. Moreover, diffusion models have been extended to conditional generation. This means you can steer the output by providing additional inputs. For example, one can condition on a text prompt or on other image-based cues for tasks like inpainting, super resolution, and style transfer. Inpainting refers to filling in missing or masked regions of an image in a plausible way, and indeed diffusion models can perform this by treating masked areas as noise to be filled. Because of these capabilities, diffusion models are a powerful backbone for image editing. They can respect complex image priors while incorporating user-specified constraints. ControlNet. ControlNet is a technique that adds stronger conditioning to a diffusion model by supplying structural or spatial guidance. The basic idea is to take a pre-trained diffusion model and augment it with an additional neural network branch that processes an input condition image. This additional branch, the ControlNet, injects features of the condition into the diffusion process so that the generated image conforms to that condition. For instance, if you feed a depth map as input to ControlNet, the output image will tend to follow the shapes and distances implied by that depth map. ControlNet thus locks in certain aspects of the scene while allowing the diffusion model to fill in other details. Researchers have shown that ControlNet can effectively enforce geometry. For example, conditioning on depth can force the scene composition and object outlines to match the given structure. In ZeST, we use ControlNet specifically to preserve the 3D geometry of the object being edited. IP adapters. An IP adapter is a module that allows a diffusion model to take an image as a prompt, in addition to text. Typically, diffusion models take text embeddings from a language model as inputs. The IP adapter extends this by using a clip image encoder. It processes a given image through clip and produces a feature embedding. This embedding is then injected into the diffusion model's cross-attention layers as an extra condition. In practice, this means the diffusion model will try to incorporate content or style from the prompt image. For example, if you have a photo of a person and feed it through an IP adapter with the diffusion model, and also give a text prompt like "in the mountains," the output will be an image of that person in a mountain setting. In ZeST, we leverage the IP adapter to extract a latent representation of the material from a material exemplar image. Concretely, the exemplar image is fed through a clip encoder. The resulting features are injected into the diffusion model when editing the target image. This allows the model to learn the appearance of the material implicitly, without requiring manual feature design. However, note that simply using IP adapters and text alone is not enough for our task. The ZeST authors found that naively combining an IP adapter with an image-to-image pipeline did not reliably transfer materials. For example, asking the model to change the apple's texture to golden bowl with a text prompt did not produce a photorealistic result, and geometry often broke down. The reason is that the IP adapter by itself entangles material appearance with object shape and context in a way that the model struggles to decouple. This motivates adding additional guidance about geometry and illumination, as we will discuss next. Depth estimation. Depth estimation from a single image is the process of predicting how far away each pixel is in the scene. Today's deep learning models can take an RGB image and output a grayscale depth map, where brighter pixels indicate farther distances. This provides a crude 3D understanding of the scene geometry from a single image. In ZeST, we use an off-the-shelf depth estimator on the input image to get a depth map of the object we want to edit. This depth map then serves as a control signal. By feeding it into ControlNet, we enforce that the geometry of the object is preserved. In other words, the model knows the 3D shape of the object via the depth, so it can keep that shape fixed while changing the material appearance. This is crucial because our method is zero-shot. We have no 3D model of the object and no explicit 3D supervision. Instead, the inferred depth provides enough structural information to guide the diffusion process. The ZeST experiments show that using depth-based ControlNet indeed preserves object geometry. Without it, the model would often distort the shape when applying a new texture. Inpainting image inpainting refers to filling in a region of an image that is masked or missing. In the context of diffusion models, inpainting is done by starting the diffusion process from an image where the target region has been replaced by noise, while the rest of the image is kept intact. The model then generates pixels for the masked area in a way that is consistent with the unmasked context. This allows one to, for example, change or replace a specific object in an image while keeping the background. In ZeST, we use a diffusion inpainting model as the core generator. Concretely, we take the input image and mask out the object whose material we want to change. That masked image is fed into the diffusion model as the initial input. At each diffusion step, we condition on the unmasked context, the depth guidance, and the material embedding. This way, the model only changes the object's appearance while keeping the surroundings and lighting consistent. An important twist in ZeST's use of inpainting is the foreground decoloring step. The authors convert the object region of the input image into grayscale before starting diffusion. Why do this? If we simply start from the original colored image, the model tends to stick too closely to the original colors, hindering the new material transfer. If we start from pure noise, the model might lose important shading cues. Starting from a grayscale version gives a balance. It removes the old color cues but preserves the object's shading and illumination patterns. The ZeST paper shows via ablation that this grayscale initialization best preserves lighting consistency in the output. In summary, the ZeST approach combines three types of input: the exemplar image, the input image's depth map, and the input image's grayscale object to drive an inpainting diffusion process. Motivation and challenges in 2D material transfer. Before diving into the method, let us clarify the goal and why it is hard. Material transfer in 2D images means, given a photo of an object and another image that shows a material, create a new image where the original object now appears to be made of that new material. This is useful in graphics, e-commerce, and design, for example, showing how furniture looks in different finishes, or editing art styles. Traditionally, achieving photorealistic material changes requires expensive 3D knowledge and manual effort. One would need to know the 3D shape of the object, the lighting in the scene, and detailed material properties. It often requires specialized tools or simulations to re-render the object with new material. The ZeST authors note that 2D material editing is especially challenging because there is no direct access to this 3D information in a single photo. Unlike texturing a 3D mesh, here we only have an image of an unknown object under unknown lighting. Key challenges include geometry, illumination, material entanglement. In a photo, the way an object looks is a combination of its shape, its material, and the lighting. If a statue is shiny, that could be due to either its material or a bright light. Disentangling material from these factors is hard. No ground truth data. There is no easy data set of real photos showing the same object with two different materials under the same lighting, which we could use for supervised learning. Collecting such data is very labor-intensive. Zero-shot requirement. The goal is zero-shot transfer. We want to take any input image and any exemplar image without retraining the model. We cannot fine-tune on each new material or object. Because of these issues, the authors emphasize that their method must be training-free and must rely on existing pre-trained models. The existing diffusion models and adapters have useful priors. ZeST cleverly taps into these pre-trained models, without further training, to perform the transfer. It is also worth mentioning why text-based editing is not sufficient. Some prior works have tried using text prompts to change an object's material. But describing the exact look of a material with text alone is hard. Text is a poor proxy for the fine-grained visual patterns and reflectance properties of complex materials. This is why ZeST explicitly uses an image of the material as a source, which provides concrete visual information. The challenge then is, how to use that exemplar image effectively. That is exactly what ZeST addresses. The ZeST pipeline. The core idea of ZeST is to decompose the material transfer task into manageable pieces. One branch deals with material encoding, another with geometry, and a third with illumination. These are then fused in a diffusion-based generation process. The pipeline is illustrated in of the paper. We will describe each component and how they fit together. We have two images, a material exemplar image M that shows the desired material, and an input image I that contains an object whose material we want to change. The goal is to produce a new image I that looks like I but with the object's material replaced by the one in M. Importantly, all other scene elements should remain the same as in I. Overview of ZeST architecture. ZeST uses a three-branch architecture, combining them within a diffusion inpainting process. Cheng.github.io. Here is a high-level summary. We encode the exemplar image M using an image encoder. This yields a material embedding M that captures the appearance of the material. We compute a depth map D of the input image I, and feed this depth map into ControlNet. This conditions the diffusion model on the object's geometry, enforcing that the final object shape matches I. We create a foreground mask of the object in I and use it to extract a foreground grayscale version of I. This grayscale image I is used as the initial state for an inpainting diffusion model. The grayscale provides shading information without original colors. During generation, the diffusion inpainting model takes these components as conditions. The material embedding M is injected via cross-attention, the depth embeddings are fed through ControlNet, and the grayscale image and mask specify the inpainting region. The output is an edited image where only the object's appearance has been changed to reflect M, while the geometry and lighting from I are preserved. We can break this down into the following detailed steps. Pass the material exemplar image M through the IP adapter's clip image encoder to get a feature vector M. This vector implicitly represents the material appearance. We will inject M into the diffusion model as a condition so the generated object looks like M in terms of texture and color. Run a monocular depth estimator on the input image I to get a depth map D. Feed D into ControlNet so that the model learns to preserve the structure indicated by D. In practice, the depth control signals ensure that the object in the generated image has the same shape and spatial layout as in I. Create a mask FG that covers the object in I, and use it to extract the foreground region of I. Convert that object region to grayscale. Call this image I gray. This grayscale version serves as the starting image for inpainting. The diffusion process will gradually refine it into the final edit. The mask FG tells the model which pixels to update. Grayscaling removes color while preserving shading, so the model sees how light falls on the object. Now we run the diffusion inpainting. The model starts with I gray and iteratively denoises. At each diffusion step, the material embedding M is injected through the cross-attention layers of the UNet. This pushes the generation towards the exemplar's appearance. The depth map D is processed by ControlNet, influencing intermediate layers of the UNet. This anchors the shape to match the original geometry. The mask FG tells the model which region is being edited. The model only changes those pixels, keeping the rest of the image fixed. The context of the unmasked background is also provided to the model. Through this process, The network produces a final image I where the object region is now in color and has the texture of M, but the object's shape and the scene's lighting remain as in I. In the paper describes this visually. Cheng.github.io. In text, the key idea is, by combining the guidance from material, geometry, and lighting with the latent features of the material exemplar, ZeST can transfer the material onto the object in the input image while preserving all other attributes. Cheng.github.io. Material encoding branch. Let us examine each branch in detail, starting with material encoding. We feed the exemplar image M into a clip-based image encoder. This encoder is part of the IP adapter module. Specifically, we take the feature vector output by the encoder and obtain a material embedding M. This embedding is a dense vector that, in some sense, captures the color distribution, texture patterns, and reflectance style of M. Crucially, we do not encode M as text. Instead, we let the image itself speak through clip. Why use an IP adapter instead of text? The paper compares to an alternative where one might do Dream Booth or another fine-tuning to convert M into a keyword or embedding. Those approaches compress the exemplar into a word-like token and then append it to a text prompt. However, they found that those text encoding approaches lose some information and can produce color shifts or fail to capture fine details. In contrast, the IP adapter lets us directly use the image. The authors note that simply using the IP adapter with diffusion without additional guidance did not work well. It often failed to isolate the material. This observation motivates the rest of the pipeline. In summary, the material encoding branch gives us one input, the latent vector M of the exemplar. During diffusion, this vector is concatenated into the UNet at each relevant layer. This ensures that the emerging object's pixels can attend to the exemplar's features and copy over textures, colors, and patterns from M. Geometry Guidance Branch. Next, the Geometry Guidance Branch. The goal here is to keep the object's shape fixed. We want the new material to wrap around the same geometry. If we ignore geometry, the diffusion model might warp or shrink parts of the object, since it only sees the grayscale initialization. To enforce geometry, ZeST uses the depth map as a strong prior. Concretely, we run a depth estimation network on the input image I. The resulting depth image D is given to ControlNet, which is a modified copy of the diffusion model's encoder that takes extra inputs. The depth image tells the model which parts of the object are nearer or farther, effectively encoding the 3D layout. Empirically, using this depth-based ControlNet makes a big difference. The paper shows that without it, outputs often ignore the true geometry, for example, trying to wrap the new material onto an impossible shape. With the depth guidance, the geometry information from the depth map overwrites the geometry information encoded in the latent, and we can successfully transfer materials while preserving original geometry. In other words, ControlNet locks in the original shape. After many experiments, the authors concluded that this simple depth-driven geometry prior was the best way to ensure fidelity. They write, "We find the depth-based guidance from pre-trained ControlNet helps us preserve the original geometry of the object for the task of material transfer." It is interesting to note that the original IP adapter paper also suggested using ControlNet, but for different purposes. Here, the purpose is purely to maintain shape. Illumination Guidance Branch. The third branch handles illumination and background consistency. Recall that we are using a diffusion inpainting model, which means we start with the input image and fill in the object region. If we simply started from a noisy canvas, the network might resynthesize background or lighting incorrectly. We wanted to preserve whatever lighting and context were already in the image I. To do this, ZeST inputs the foreground grayscale image as the initial condition. That is, we take the input image I, mask out the object region, and replace those pixels with a grayscale version of themselves. The background remains as before. This grayscale foreground ensures that the model knows the object's shape and shading but has no color bias. The diffusion will then colorize and texturize the object according to the material embedding, but it will do so in a way that is consistent with the object's original lighting. Technically, ZeST uses a diffusion inpainting model. This model takes 4 inputs: the material encoding M, the depth map D, the initial image I gray, the foreground mask FG. The inpainting model is conditioned on all of these. Practically, I gray is the noisy image to denoise at the start, and FG indicates which pixels should be changed. The diffusion then proceeds only in those masked regions, treating the rest of the image as context. This way, the illumination in the input is largely preserved. If the room had warm light coming from the left, that lighting effect remains on the object as its surface changes. The ZeST paper includes an ablation showing that using the grayscale foreground yields the best results in terms of correct lighting. They explain, using the original color biases the model too much, and pure noise loses shading clues. The grayscale strikes the right balance. After setting up these branches, the actual image generation is straightforward. Run the diffusion inpainting with all these conditions. Importantly, ZeST is training free. It uses pre-trained networks, the clip/IP adapter, a monocular depth estimator, the ControlNet, and the diffusion model. No part of this pipeline is fine-tuned on new data. As the authors emphasize, the method works on real images without any training, resulting in a zero-shot approach. The pipeline is fast. Since no learning is involved, once all modules are loaded, ZeST can generate an edited image in on the order of 10 to 15 seconds. In contrast, methods like DreamBooth require minutes of fine-tuning for each exemplar. The target object must be identified to create the mask. ZeST uses a simple foreground extraction to isolate the object. For more complex scenes, they later show it can use segmentation models like SAM. All components are differentiable, but no end-to-end gradient updates are done. It is purely a feed-forward use of each model. Experimental setup to evaluate ZeST. The authors curated 2 types of data sets: real-world dataset, 30 material exemplars paired with 30 input images. These were collected from copyright-free sources and from images generated by DALL-E 3. Each exemplar shows a clear material on an object. Each input is a different object onto which the material is transferred. This dataset tests the method's performance on diverse, challenging real images. 90 images created in Blender for quantitative evaluation. The authors took 9 distinct materials and 10 3D meshes. They rendered each mesh once per material, giving 90 rendered images. In addition, they rendered a sphere with each material to serve as the exemplar material image. This synthetic setup gives a clear ground truth: the sphere's material is exactly the same we want on the object. Thus, metrics like PSNR and LPIPS can be computed between ZeST's output and the ground truth render. Since ZeST does not require training, the dataset sizes are relatively small. The authors note that the scale is comparable to prior work that did diffusion fine-tuning for texturing. Baselines for comparison. Material transfer from a single image is a novel problem, so there are no direct prior methods. The authors construct several baselines by combining existing techniques, IP adapter plus instruct pix 2 pix. Here, they use the IP adapter to encode the exemplar, but instead of ZeST's geometry/illumination pipeline, they try using instruct pix 2 pix to apply the change. Essentially, change the texture of the object prompt. This is more of an ablation to see what happens if we drop geometry guidance. DreamBooth plus instruct pix 2 pix. First train a DreamBooth on the exemplar images to create a special token for the material, then use that in a text prompt with instruct pix 2 pix. This is similar to some mesh texturing pipelines. DreamBooth plus Mossa control, DreamBooth for material token, then use Mossa control to apply it. Run ZeST's full pipeline, but replace the IP adapter embedding with a text token. This tests whether the image prompt embedding is crucial. No IP adapter or depth, just do standard inpainting with a text prompt for texture, to show the effect of losing geometry control. The key comparisons are to check if our specialized material pipeline outperforms these more generic editing schemes. In particular, Dream-Booth-based methods require poor exemplar training, making them slow and less practical. ZeST's goal is to avoid that. Experimental results, qualitative results. ZeST produces visually compelling results across many scenarios. The paper shows dozens of examples demonstrating that even with complex shapes and lighting, ZeST can successfully map one material onto another object. Some observations from those examples: in almost all cases, the object's shape is clearly maintained. For instance, a statue's face remains the same, only its surface texture changes from marble to metal. The shading and highlights on the object make sense given the scene lighting. If the exemplar is shiny and the input object is curved, you see appropriate specular highlights. In the car example, a matte car becomes shiny brass, and you see new bright highlights in plausible places. Specular/gloss effects: when transferring to a shiny material, the model adds specular reflections. The paper notes that for the brass car and steel dinosaur, the bright spots on the object change to match the exemplar's shininess. Similarly, adding glass or plastic finishes introduces appropriate gloss. Some materials are flat while others have patterns. ZeST correctly handles both. E.g., an orange toy gets a completely flat metallic paint, whereas a patterned exemplar yields visible texture. Remarkably, ZeST can handle transparencies to some extent. For example, in one case, an exemplar showing colored glass is transferred onto another object, and you can faintly see the background through it. The model managed to apply the notion of transparency. Even when the exemplar includes extraneous objects, ZeST tends to ignore the irrelevant parts and focus on the main material surface. This shows robustness in extracting just the material appearance. ZeST is compared side by side with the aforementioned baselines on several examples. The differences are striking. Methods without explicit geometry guidance mangle the shape. The object may be resized, warped, or replaced by a new object that vaguely matches the prompt. They effectively ignore the original object geometry. Instruct-Pix-2-Pix tends to preserve shape, but it fails to capture the material accurately. The output may not look like the exemplar material, it often just recolors or lightly textures the object. The combination of Dream-Booth plus MOSA control often misattributes the material and also distorts geometry. For example, a material meant for a mug might be spread incorrectly onto a backpack. The closest baseline is Dream-Booth plus ZeST's geometry/Illum branch. In this variant, they use Dream-Booth to encode the material into a text token, but still use the depth ControlNet and inpainting from ZeST. This often produces reasonable transfers, but the results have color shifts and less fidelity. For instance, the backpack example has a slightly wrong hue, and the astronaut figure has some color bias. The authors attribute this to information loss when compressing a visual material into a word embedding. ZeST, by contrast, consistently preserves geometry and lighting while accurately applying the material. Across examples, ZeST performs the task effectively and retains fine details of both shape and illumination. Notably, ZeST handles the challenging transparent and occluded cases better than baselines. In summary, qualitatively, ZeST achieves the desired edit without unwanted side effects. Other methods either fail to apply the material correctly or break the scene. An important practical point: ZeST is very fast at test time, whereas Dream-Booth variants would need minutes to fine-tune per exemplar. Quantitative results on the synthetic data set: the authors report standard image quality metrics, higher is better, measures per pixel similarity to ground truth. Lower is better, a learned metric capturing perceptual differences. Cosine similarity between clip embeddings of output and ground truth, higher means more semantic/visual similarity. They compare the two strongest baselines from qualitative tests, IP Adapter plus Instruct-Pix-2-Pix and Dream-Booth plus ControlNet inpainting. The results are: Method PSNR LPIPS ClipSim IP adapter plus instruct PIX 2 PIX 16.920.0960.745 Dream Booth plus Geo/Illum Guidance 25.460.0530.893 ZeST 25.820.0460.899 ZeST achieves the highest PSNR and lowest LPIPS, and the best clip similarity. In practical terms, this means ZeST's outputs are quantitatively closest to the true material renderings. The gap versus the instruct-based baseline is very large. ZeST's PSNR is 9 points higher, and LPIPS 0.05 lower, indicating much better fidelity. These numbers validate that the geometry plus illumination guidance is critical, and that compressing via text loses quality. Additionally, a user study was conducted on real images. 16 participants each rated random edited images on 2 criteria from 1 to 5, material fidelity, and photorealism. The average scores were, Method Material Fidelity Photorealism IP Adapter plus Instruct PIX 2 PIX 1.483.23 Dream Booth plus Geo/Illum Guidance 3.25 3.41 ZeST 4.05 3.78 ZeST significantly outperforms the other methods in both metrics. The jump is especially large from fidelity 3.25 to 4.05. This confirms that users find ZeST's material matches the exemplar much better than the baselines. The improvement is even more pronounced in real-world images than in synthetic, possibly because baselines like Dream Booth overfeed to synthetic conditions. These quantitative and human results strongly support ZeST's effectiveness. It achieves near the best possible scores among comparable methods, without any fine-tuning, and with practical speed. Robustness. The authors also test ZeST's robustness to variations in the exemplar. 2 experiments highlight this: lighting/pose changes of exemplar. They took one material, and rendered it 3 times under different lighting directions and rotations. They then used each of these as the exemplar to transfer onto the same target. ZeST's outputs were roughly consistent across these variations. That is, even if the exemplar image had different shadows or orientation, ZeST extracted the underlying material appearance reliably. This suggests ZeST is not oversensitive to the precise capture of the exemplar. They tested what happens if you zoom into the exemplar so that only a small portion of a repeating texture remains visible. The exemplar was a cloth with a distinct weave pattern. When they zoomed in so that very little pattern was visible, ZeST still transferred the pattern to the chair, automatically adjusting its scale to fit the target. In other words, ZeST infers the texture scale from context. This is likely because the diffusion model has seen such textures at various scales, and the latent embedding plus context cues guide it to a reasonable size. These tests indicate that ZeST can handle some real-world variability. The exemplar need not be perfect, and the method still works if the exemplar is differently lit or partly cropped. Applications beyond basic single-object editing. ZeST enables several interesting use cases. ZeST can be iterated to apply different materials to different objects. The trick is to replace the simple foreground mask with multiple masks using a segmentation tool like SEM. Then for each object/exemplar pair, run ZeST with that mask. The paper shows examples where, say, a bowl's material and a chair's material are changed independently in one image. Because each object is masked and edited separately, they do not bleed into each other. Of course, if one object's new material reflects another, the order can matter. The authors note it's best to apply reflective materials last so that reflections can capture other edits. Exemplar-based 3D texturing. ZeST can be integrated into pipelines for texturing 3D meshes. The authors mention text-to-text, a method that textures meshes using stable diffusion and ControlNet with text. They simply replace the text prompt in text-to-text with an image exemplar input to ZeST. The result is that a 3D model can be textured by exemplar images. They show, for example, a Porsche and a backpack mesh each textured using 2 different exemplar images. Even when the exemplars were not the same shape, ZeST correctly applied the patterns according to geometry. They also found that adding a descriptive text prompt helped ensure consistency across multiple views. This application is powerful because it means one can use a single exemplar photo to guide multi-view texturing of a model, without Dream Booth. It's much faster and more direct. Lighting-aware material transfer, ZeST can also be used to simulate how a material would look under different lighting. The authors describe a procedure. First, apply ZeST to generate the texture of an object under one lighting condition. Then, keep the random seed fixed and rerun ZeST on the object rendered under a second lighting, using the first output as the exemplar. This way, the material appearance stays consistent, but the reflections adjust to the new light. They demonstrate this by transferring the material of a glazed cup between two mesh renders with different illumination. The result is that the patterns on the cup stay the same, but the highlights move according to lighting. This suggests ZeST implicitly models how materials reflect light, so it can re-render textures consistently. It opens up possibilities for relighting an edited image. In summary, ZeST is not just a toy, it can be plugged into practical editing pipelines, multi-object editing, and even 3D texturing. The key enablers are its zero-shot nature and reliance on standard pre-trained components. Limitations: no method is perfect. The paper identifies a couple of recurring failure modes. Sometimes ZeST only applies the new material to part of the object instead of the whole thing. For example, a jacket material might only show up on the torso of a statue but not the legs. The authors hypothesize this is due to entanglement. The model thinks this part of the exemplar looks most like the object, so apply material there. Essentially, the IP adapter doesn't segment the exemplar, so if the exemplar has variations or multiple zones, ZeST might focus on only the dominant one. This leads to incomplete transfer. If the exemplar image itself contains more than one material or object, ZeST can get confused and blend them. For instance, a tennis ball exemplar might show both the fuzzy yellow and the white logo part. ZeST might mix these when texturing the target. This again is due to the image prompt containing multiple regions. Since the IP adapter just encodes the whole image, it doesn't know to separate them. Operating purely in latent space can lead to small, hard-to-control behaviors. Since we never optimize or supervise ZeST on a loss, it relies on the diffusion priors. Occasionally, it might hallucinate patterns or colors that look plausible but weren't exactly in the exemplar. The authors note these as areas for future work. Perhaps combining ZeST with segmentation or with a learned mask of the exemplar material could help isolate single materials. But despite these limitations, ZeST works surprisingly reliably in many cases. The failures shown are instructive but relatively rare compared to the successes. Conclusion: to recap, ZeST is a zero-shot, training-free method for transferring material appearance between images. It is built entirely from existing pre-trained components, a diffusion model for inpainting, a clip encoder via IP adapter, a depth estimator, and ControlNet. The magic is in how these are combined. ZeST encodes the exemplar's material in latent space, uses depth to lock geometry, and uses grayscale inpainting to maintain lighting. The result is a photorealistic edit that convincingly changes an object's material while leaving everything else unchanged. Experiments on both synthetic and real datasets show that ZeST outperforms alternatives. It produces high PSNR/LPIP/clip scores on ground truth synthetic renders, and users rate it higher in material fidelity and realism on real images. It is robust to changes in the exemplar and generalizes to multi-object and 3D texturing scenarios. ZeST's main contribution is showing that complex image editing tasks, like material transfer, can be done by cleverly harnessing frozen generative models. No new training data or learning is needed. The authors position this as a strong starting point. By leveraging the rich priors in diffusion models, we can tackle challenging graphics tasks in an intuitive way. In conclusion, ZeST demonstrates that zero-shot material transfer is feasible. It opens up new possibilities for content creation. Designers can swap materials in photos with a click, 3D assets can be textured from photos, and graphics editors have a new powerful tool. The approach of combining image prompt embeddings, geometry control, and inpainting may inspire other zero-shot editing methods. As diffusion models and their adapters continue to improve, we can expect even more impressive, flexible editing workflows based on ideas like those in ZeST.